Hey guys, in this video we will implement the Yolov8 detection model from the scratch, explore its underlying structure and gain a deep understanding of how it works. In creating this video, I have used reference from the following resource. So there are 3 of them, 2 of which are GitHub repo and 1 is an archive article. First, we will look at the Yolov8 model structure. Like any modern model, Yolov8 has 3 parts: the backbone, the neck, and the head. The backbone is used to extract useful features from the input image. The neck is used to process those features, and the head is used to give predictions. Before we go into the code, we will look at the original Yolov8 model and see how many parameters are there. So here I load Yolov8 from Materialistic, and here for inspection we will load the nano model. We can see that this model has 3.15 million parameters, and here are all the layers. So in creating this model later, I will try to match all the parameters, for example epsilon and momentum here. So let's first create the backbone of Yolov8. I should note that even though this picture is a very nice pictures, which give me the idea on how to create Yolov8, but it should, based on what I have experienced, it only match the nano model. The other model seems a little off in the number of parameters. So when we look at the backbone, let me zoom out, we can see that it is a sequence. It consists of blocks, convolution, C2F, and SPPF as the last one. The convolution here consists of the usual convol2D, batch norm, and activation CLO. For the C2F, we start with convolution. We split the input into 2 parts. One part we feed through a sequence of bottleneck layers, and after that we concatenate the output of this one with the residual connection here and feed through another convolution. For the SPPF, we start with convolution. We feed through 3 layers of maxpool2D, and together with some residual connection, we will feed through another convolution. So let's go into the code and create the backbone of Yolov8. So here, as mentioned, the backbone consists of the 3 blocks, and we will first implement the convolution block. Here I have already written now some code. So our convolution block take in the in channel, out channels, kernel size, stripe padding, groups, activation is set to true. So the convolution here is convol2D with in channel, out channels, kernel size, stripe padding, bias equal to false, group equal to groups. The batch norm here is the batch normalization on the out channels with this specific value of epsilon and momentum. Here the activation function is CLO and n.CLO in place equal to if activation else nn.identity. So when we forward the data, we will forward through the convolution and then apply batch norm and apply activation. So we return self.activations, self.batch normalization, self.convolution of the data. So the convolution block is pretty straightforward. The less straightforward one is the C2F, which is called cross-stake partial block cross-state partial bottleneck with two convolutions. So we have the first convolution, we have a sequence of bottlenecks, and we have the second convolution. What this block does is it combines high-level features with contextual information to improve detection accuracy. So here is a picture for the C2F. We start with convolutions with the specified parameters, and then we will split the data into two parts. Half of them is fed through a sequence of bottleneck layers. The other half is kept for residual connections. And at this point, we concatenate the output produced by the bottleneck layers and the part that was saved earlier, and we feed through another convolution. So the number 2 here means we have two convolution layers. So the main thing that we need to implement in this case in order to implement C2F is the bottleneck layer. So here the structure of bottleneck layers. So bottleneck layers, there are two types. One has shortcut equal to true, and the other has shortcut equal to false. For the one with shortcut equal to true, we have two convolution block, and then we have residual connection. For the other case, we only have two convolution block without residual connections. So here we will implement C2F, but first we will implement, let me say this is 2.1. We will implement the bottleneck. The bottleneck here is a stack of two convolution with shortcut connection, which can be true or false. So we will create class bottleneck. We will init with the in channel, out channels, and shortcut here is set to true. We do a super init. So we have two convolution block. The first one, convol, in channel, out channels. The kernel size that is used is 3, stride is 1, and padding is 1. For the second convolution block, we have out channel to out channels with the same kernel size, stride, and padding. Another attribute we need to set is shortcut. Shortcut equal to shortcut. So now we will define the forward pass. So if we look back here, in the case that is short, we just feed the input through two convolution block, and in the case there is shortcut, we will keep a copy of the original input and add with the output. In the case there is no shortcut, we just return the output. So here we will keep a copy of the input for residual connection, and now we will feed the input through the convolution block. Should be number 2. The first block, the second block. If there is shortcut, we add the residual connection. Now we return X. So once we have this bottleneck, we now can write the C2F, which is convolution with stack of bottleneck, let's say n of them, and convolution block. So I call this C2F. We will do an init. So here we need to have in channel, out channels, number of bottlenecks, and shortcut for the bottleneck. We do a super init here. So let's look back to the structure of C2F. So here first we will pass the input through the first convolution block, split it into two equal parts. One part is kept for residual connection later, and one part is fed through a sequence of bottleneck layers. And at the last step here, we will feed through the second convolution block to give the output. Well, so here I will, because we are going to split into two equal parts, so I will define the mid channels to be half of the out channels. So maybe just self.mid channels is half of the out channel. And we have other attribute like number of bottlenecks equal to number of bottlenecks. We have two convolution block, in channel, out channel. Well, for this convolution block, we have kernel size equal 1, stride equal 1, and padding equal 0. That is the first one. For the next part, we get a sequence of bottleneck layers. So self dot bottleneck, or this is self dot m to say this is a modulus, is nn dot modulus of bottleneck, which take in channel equal to the mid self dot mid channel, and we repeat number of bottlenecks of them in range number of, well, this should be in range number of bottlenecks. So this is our sequence of bottleneck layers, and the last one is the second convolution block. So for the second convolution block, here at every step of bottleneck we have an output, and we will keep the output, and at the end here we concatenate the output from all the different levels, and in doing that concatenation we have this output with the channels, number of channel equals 0.5 times n plus 2 times C out. So this I will copy this number in defining this convolution block. The out channel is still C out. So here we have number of bottlenecks plus 2 times out channel divided by 2, and we have out channels kernel size equal 1, stride equal 1, and padding equal 0. Alright, and now let's do the forward. So first we pass the data through the first convolution, and at this step we need to split it along the channel dimension. So the channel dimension is the second dimension. The first one is the batch dimension. So we have x1, x2, where x1 is half of the channel of x. The last two dimensions are width and height. x2 will be the rest of the channel of x. And now we will have a list for output, because later we are going to concatenate the output. So this list will start with x1, x2. So note that here x1 will be fed through the bottlenecks. So now we will feed x1 to the bottleneck. So for I in range number of bottlenecks, x1 self dot m I x1. Well, note that I should have mentioned that each of x1 and x2 here has number of channel equal half of the original one. So at this point, the shape of x1 should be batch size times 0.5 of C out, width and height. So here we will insert this into the output, and the final output will be not the final output, but at this step we are going to concatenate everything that we have obtained along the channel dimensions. Well, note that here each of the bottleneck give output with 0.5 C out. So when you do concatenation of all these, you have 0.5 C out times the number of bottlenecks, and we need to plus with 2, which is the original output. 2 here means C out, because x1, x2 together has out channel C out. So at this point, the shape for the output will be 0.5 C out, number of bottlenecks, plus 2, and width and height. Finally, our output or out is self convolution 2 on the outputs, and we'll return this value. So that is our C2F block. Let's do a sanity check here. So let's say we have C2F with in channel equal to 64, out channel equal to 128, number of bottlenecks is 2. Let's print out the number of parameters for P in C2F dot parameters. We print out in million parameters. Let's have an input and compute the output produced by this C2F layer. So let's say a dummy input is just dot random 164, maybe 244. So the in channel is 64. So dummy input should go with dummy output C2F. Let's print the output shape. So the output shape here is simply dummy output dot shape. All right. Invalid decimal literals. Sums of looks, oh, here, this is an error. All right, so now you can see this C2F block has 0.19 million parameters, and when we feed in this input with channel dimension 64, the out channel dimension is 128. It looks good. So now the third type of block that we need in order to implement this backbone is the last one here, SPPF. Well, SPPF here is called Spatial Pyramid Pooling Fast. So it basically processes features at various scales and pull them into a fixed size feature map. So as can be seen from here, we have max pool, which reduce the feature size, and at the end we concatenate the feature at different levels. So we have two convolution together with 3 max pools. Now we will implement SPPF. So here we will need to init with the in channels, out channels kernel size is equal to 5. It should be noted that in this case the kernel size is a size for max pool, not the kernel size for the convolution block. So we do a super init. When we feed the input, we will feed to the hidden channels equal to half of the in channels. So here we set hidden channels equal half of the in channels, and we will define the first convolution to be a convolution block from in channel to hidden channel with kernel size equal to 1, string equal 1, and padding equal to 0. Note that we concatenate the output of max pool and feed to the second convolution. So by doing this for the second convolution, it take in the in channel equal to 4 times of the hidden channels to the out channels, because we have three max pools, and here the kernel size is 1, string equal 1, and padding equals 0. Now is max pool. The max pool layer is applied at 3 different scales. It's applied at 3 different scales, which means 3 different inputs. So self max pool, and then max pool 2D, kernel size equal kernel size, in this case equal to 5, string equal 1, padding is kernel size over 2, because we want to keep the dimension of the output to be the same. We set relation to 1 and ceiling mode to false. Well, I haven't, we have a self here, and now we will do the forward pass. So So first we will feed the input through the first convolution. We apply mux pooling at different scale. So let's say y1 is the first mux pooling, output of the first mux pooling. Y2 is the output of the second one, and Y3 is the output of the third one. And we will concatenate all the output. Touch cat x, y1, y2, y3, and we feed through the final convolution. Convolution 2, and return y. Let's have a quick check here. Let's say well, SPPF, we take in channels equal to 1 to 8, out channel equal to 512. Let's print out the number of parameters. Here again we print out in million. Let's have some dummy input again. Well, I can just take this. And so here I should take in channel dimension equal to 1 to 8. Well, why not just keep going on from the last one? So here we will take the output of this layer and feed it to the SPPF, because that just follow the model structures. So here change this to dummy input, and we'll use it for the next one. So now just keep the same name, dummy input, and we will print out the shape. Alright, invalid decimal. Okay, I forget 6 again. We got 1 to 8 channels instead. So here the arrow come from me using the earlier module, so I should have used SPPF. So now we can see it runs correctly. The SPPF has 0.14 million parameters, and in this case the output has out channel equal to 512. Next we are going to put everything together and code the backbone. So here I think it could be a good idea for me to put the figure on one side and the notebook on another side. This figure I don't want to move. So here we can see the flow of the data. So we start with 2 convolution block, C2F, convolution C2F, and so on. Note that in this case the output of the backbone has 3. One part is at the layer number 4, one part at layer number 6, and the last one is at the last layer. So here let me rescale it so I can refer to the picture. Let's put everything together here. So backbone is modified versions of .NET 53. First let me just code out the parameter of Yolov8. because in this you see the n here, for example, the n here is the number of bottleneck layers equal to 3D, where the parameter d is a parameter which is defined here. D is depth, and its value depends on whether we have nano, small, medium, or large models. So here they have different values, and we also have width and r. So let me just write a function which return these values for corresponding nano, small, medium models, and so on. So if version is nano, we return d is 1/3, 1/4, 2.0. So here let me just write it out. So return dwr, which are called depth width ratio based on version. So this is the case where we have nano version. Now if version is S, we return 1/3, half, and 2. Or if version is M, we will return 2/3, 3/4, and 1.5. Let me make sure I don't copy the wrong number. This is 2/3, 3/4, and 1.5. The next one 111, and the last one is 1.25, and 1. For the L model, we have O1, and for the X model, we have 1, 1.25, and 1. So these are the parameters. So now we will put everything together to create the backbone of Yolov8. So here we will init with the version. In channel we will default it to 3. Shortcut for the bottleneck layer, default to 2. Super init. So first we extract dwr by calling on the Yolov parameter versions. So well, let's look at here. For the first convolution here, we take in channel equal to 3. The out channel is 64 times W. So our self convolution 0. So here I just index that I try to index that match with this layer number 0, 1, 2, and so on. The first convolution self convol 0 is convolution layer with in channels. Our channel is 64 W, kernel size equal to 3, try equal to 2, padding equal 1. The next one, convolution 1, take in channel equal to 64W. Our channel is 128W. Same K, S, and P. So the next convolution block is here. I will index convolution 3 just to match with the layer number 3 here. 128 is the in channel, and now channel is 256. 128. 256. We all have KSP equal 3 to 1 for all the convolution block. And the next one is the layer number 5, where in channel is 256W and the out channel is 512W. And the last one is in layer 7, where the in channel is 512W and the out channel is 512 times W times R. So these are all the convolution layers. So next we have C2F layers. Yeah, let's put here. The first C2F layer is in layer 2. So index C2F2. The in channels here is 128W. The out channel is also 128W. The number of bottlenecks here, number n here, is equal to 3D. And shortcut in this case is set to true. That is the first C2F. The second C2F is at layer number 4 with 256W, 256W as in and out channels. Number of bottlenecks is 6D and shortcut equal to true. The next C2F is at layer 6, where we have 512 as in channel and 512W as the out channel. Number of bottlenecks is also 6D and shortcut is true. The last C2F is at layer number 8, where the in channel is, in this case, 512WR and out channel is also 512WR. Number of bottlenecks is 6D. No, it's, well, in fact, I have worked through this and I think there is a typo here. Number of bottlenecks should be 3D. Otherwise, later when we create the model, the number of parameters will not match with the official Yolov model. So here there is a typo. And the last block is SPPF. SPPF is SPPF with in channel is 512WR and out channel is here. So here we have the out channel is also 512WR. So this is not the out channels. So I've lost my mind a little here. So let me check on SPPF. Yeah, the out channel is also 512WR, sorry. Alright, so that is all the attribute I need to initialize. Now let's define the forward pass. So first we feed to the first layer, which is a convolution block. Feed through the second one, which is another convolution block. And the next one is a C2F. C2F2. The next one is a convolution block, convolution 3. The next one is another C2F, but note that at this one we need to keep a copy for the output. So X C2F4 X. Well, let's say maybe out 1 because we want to keep this for the output. And keep for output. The next one will be convolution block, should be convolution on R1. And for the next one we also need to keep for the output, so I will put R2. R2 is C2F6 on X, keep for output. And then the last three here, X self dot convolution 7 R2 self C2F should be C2F8. There's typo here. C2F8 X and SPPF. We will, so this should be R3. We'll return out 1, out 2, out 3. Let's do a check. Let's say, well, let's check on different model. So here we have nano model. So let's say backbone of the nano model is backbone version is nano. Yeah, and we will print out the number of parameters. F strings sums for p in backbone dot parameters 1e6 million parameters. And let's have the small versions. And we also want to print out the number of parameters for the backbone of the small version. Yeah, so let's see. Okay, so the backbone of the nano model in this case has 1.27 million parameters, and the small one has about 5 million parameters. We also want to have a sanity check. Let's have an input as random, let's say like random pictures with resolution 640 by 640 with 3 channels, and we have 3 output. When we run through the backbone nano, we will print all the output shape. Say output 1, output 2, and output 3. So here we have 3 output at different resolution and also different channel dimension. So that's it for the backbone. Next we are going to implement the neck layer, the neck of the Yolov model. So here if you look at this paragraph, you can see that the neck here consists of C2F, which we already coded, upsample, and here we only need to have upsample. What is upsample? Well, look like they don't have it here, but I rewrite out. Upsample here is a nearest neighbor interpolation with scale factor equal to 2. So we are going to code this upsample block and get the neck of Yolov8. So this upsample we will init with a scale factor equal to 2. The mode of interpolation here is nearest. Attribute self dot scale factor equal to scale factor self dot mode equal to mode not mode. For the forward, we simply use the built-in nn dot functional dot interpolate the input at this scale factors self dot scale factor with the mode equal self dot mode. All right. So now we will code the neck layer. So class neck and dot module. So here we have parameter which lie in the versions. So here first let's extract the parameters from the version. Let's look at the structure of the neck here. So here we can see the neck here comprise, it start from here, go in this way. So we will flow the data in the same way as the diagram. I'm not sure why this cannot be smaller. All right. So we have an upsample block. Note that this block have no changeable parameters, and we have all the C2F here. So I will try to match C2F, the first one. So for the first C2F here, the in channel is 512W times 1 plus R. 512W 1 plus R, and the out channel is 512W. And the number bottleneck is 3D. Shortcut is false. That's the first one. For the next one, we have in channels here 768 W. We have out channels equal to 256 W here. Number of bottlenecks equal to 3D. Yeah. Shortcut is false. And the next one, C2F number 3. Next one is here, down here. So well, why not make a copy? In channel 768W, out is 512. number of bottleneck is also 3D. And the last one, for the last one, in channel phi child W times 1 plus R out phi child WR and the number of bottlenecks is also 3D. Right. So all these are the C2F block. Here we also have convolution blocks. We have 2 of them. So self convolution 1. The in channel for the first block is 256W. Out channel is also the same. Kernel size equal to 3, string equal to 2, and padding equal 1. For the second one, phi 12 to phi 12, phi 12W to phi 12W. With kernel size, string and padding are the same. So those are all the blocks that we need. Now we are going to do the forward pass. So forward self X. So here I should be careful because the neck here take input from the backbone, which has 3 parts. So I will call them X residual 1, X residual 2, and X. So the residual 1 come from here, residual 2 come from here, and X come from the last layer. Here I should note down that these 3 are output of the backbone. So the flow of the data is from X here all the way up and down. The output of the neck, there will be 3. One is at this point, the other 2 are at 2 other different levels. So first, here from X here, we have 2 paths. One we go up and one we go to this layer number 20, where from here we will give output at the 3rd level. So we need to keep 1 copy for the connection letter, and 1 copy will be flow through the neck. So here I will call the copy that we keep is residual 1 equal to X for residual connection letter. And now we will flow X in this way. So X equal to self dot up X, and we will concatenate X with the residual 2, X residual 2 along the channel dimension, and then we will pass through the C2F. Note that at this point the output of the C2F will be fed through the next layers, and one of the copies will also be kept for residual connections. So in this case we need to keep another residual connection, so I call residual 2 equal to self dot C2F first layer on X. So for residual connection, and now let's go up. X equal to self dot up on residual 2, and we will concatenate. At this point, we will concatenate x with the x residual 1 along the channel dimension. At this point, we will feed through the C2F, and we have that as one as output, and the other one will be flown down below. So let's keep it here. We have out 1, C2F number 2 on X, and so that is one output. The other one will be flown down here. So next, X will be self dot convolution. Now I call it CV1 on L1, and we will concatenate this with the output from here. So X is touch dot cut of X and residual 2 along the dimension 1, and we'll feed through C2F. We had another output which I call out2, C2F, which should be C2F3, C2F3 on X. So we have the second output, and now we will continue to feed it through the convolution CV2 L2. We will concatenate this, and then we will concatenate with the residual connection from here. So X equal to touch dot cut X residual 1, and at this point we get the third output, L3, C2F4 on X. So now our output will be out 1, out 2, and out 3. Now let's do a sanity check on our model on the neck. So here we will have the neck of the nano model. Let's print out first the number of parameter. Meaning parameters. Let's start from, let's say, random image with resolution 640 by 640. We pass the image through the backbone. We also need to create the backbone. Say backbone with the same version on X, and we get the output by applying the neck on the output of the backbone. Let's print out the shape of the output. So 2 and 3. Right, neck get an unexpected keyword version. Self version. Version is a wrong pronunciation. Right, so we can see here the neck is about 1 million parameters, and the output, there are 3 of them at different resolution and also different channel dimension. Well, at this point, I have noticed that my video can get too long if I keep doing it this way from coding from the scratch. So for the head and for the training of the model later, I will code it before and we'll just go through important details. Now we will study the head. In this figure, the head consists of only two parts. One is responsible for bounding box coordinates and one is responsible for classification scores. However, in the official implementation of Yolov8, the head should have three parts: one for bounding box coordinates, one for classification score, and one for the so-called distribution Foucault laws that will be used to generate the refined coordinates for the bounding boxes. So this figure is not very updated. So let's go to the notes here and I will explain about what is distribution Foucault laws. It's pretty clear what are bounding box coordinates and what is classification score. What about distribution Foucault laws or DFL? What DFL does is that it considers the predicted bounding box coordinates as a probability distribution, and at inference time it will sample from the distribution to get refined coordinates for the bounding boxes. Let's say the coordinates, the output for the bounding box coordinates are x, y, w, h. For example, to predict the coordinate x in a normalized range, let's say from 0 to 1, DFL first use 16 bins which are equally spaced between 0 and 1. So in this case, the bin length is 1/16. The model will output 16 numbers which correspond to probability that x fall in these bins. And here let's take an example where the first 14 numbers are 0, the last two are 9/10 and 1/10. So in this case, prediction for x will be the mean value based on these probabilities and based on the fixed bins. So we have 9/10 times 15/16 plus 1/10 times 1, that is 0.94. With this in mind, we will look through the code that implement DFL. So here, the default number of bins that is used is 16. So here, CH means the number of bins equal to 16. And for the computation, for I guess the reason here is for fast computation, we initialize the self-convol as a convolution layer that has in channel equal to 16, out channel equal to 1, which is the value of the bounding box coordinate, kernel size equal 1 without bias, and we don't require gradient. So note that DFL is only used in inference time. It is not used in training. So only at inference time we get refined coordinates of the bounding boxes. So we don't require changeable parameter for DFL. So here the weight of this convolution layer will be from 0 to 15. So we purposely initialize the convolution layer to have weight from 0 to 15 as indicated in these two lines. So now let's say we have input x. Note that this input must have number of channels equal to 4 times the number of bins, that is 64. We will reshape x so that it come in the shape batch size 16, 4, and 8. We will take the softmax on the channel dimensions to get the distribution probabilities. By doing that, now the channel dimension here contain 16 probabilities, and we will apply the convolution that is defined before on these probabilities. Note that the weight of the convolution in this case are fixed between 0 to 15. So when we apply that weight on the probabilities, we get the mean for the bounding box coordinate. And here at this point, we get the mean for the bounding box coordinates, and we will return the value. And here for sanity check. We get some dummy input. We initiate DFL. Let's try to print out the number of parameters. We in this case we have 16 parameters, but they are not changeable parameters because we set required grad to be false. Yeah, as can be seen, there are 16 parameters. Output dimension is 14128, and here is the DFL. Now we are in for the head of Yolov8. Let's look at the picture again. So for the bounding box, we have two convolutions block and one convolution layer. For classification, we also have two convolution blocks and one convolution layers. On top of this, we also have distribution focal loss. So here, the attributes are versions. The number of bins, which is channel, equal to 16. Number of class denote the number of class for classifications, and in COCO dataset it is 80. So first we initiate the attributes. So self.coordinates here mean the number of bounding box coordinates, and that is equal to 16 times 4, which is 64. And self dot number of class here is 80 because we use the COCO dataset. And self number here means the number of bounding box coordinates plus the number of class. So in this case, it is numbers of outputs per anchor box. The stride here are used during build, during training, and we will extract depth, width, and ratio based on the versions. So here we have 3 modules for box, for classification, and for DFL. For bounding box, we have a module list of 3 layers. The first one is a sequential layers with 2 convolutions block and 1 convol 2D. So this one is for the first detection head. For the second detection head, we have another sequential of 2 convolution and 1 convol 2D. And for the third detection head, we also have 2 convolution and 1 convol 2D. For classification, we have 3 detection heads, which so we need also 3 layers which correspond to these 3 detection heads. So each of them have 2 convolution block and 1 convol 2D. And for DFL, it's just the normal DFL. So here is the forward pass. Note that at this point, X is the output of the neck, which is the list of 3 tensors at different resolution and different channel dimension. So X here is a list of X0, X1, and X2. So for each of these, if we look at the figure again, let's say this is X0, X1, X2, and each of them will be passed through a separate detection head. So for I in range, here is just range 3, we will pass Xi through the detection head I. So we pass, we get the box, we get the classification score, and the output will be the concatenations of the bounding box coordinates and the classification score along the channel dimensions. So the output Xi here has shape number of coordinates plus the number of classes on the channel dimensions. So note that in training we do not give any output for the DFL, so we just return X in training. And in this case, X is the list of X0, X1, and X2. So in terms of shape, it has shape 3, batch size, number of coordinates plus number of classes, and WH. In inference time, DFL produce refined bounding box coordinates. In order to have these refined bounding box coordinates, we need to have anchor points and strides that come from the function make anchors. So let's first skip this one and see what the function make anchors does. So the function make anchors here return a list of anchor centers together with the strides. So in terms of input, X is a list of feature maps, let's say x0 up to xn-1, and in our case X is just the n here is the number of detection heads and equal to 3. So X is a list of 3 feature maps. Each of the feature map here having shape of the form, batch size, channel dimensions W and H. And for the output of this function, each feature map will give an output where we have W by H anchor coordinates and W by H stride values. What are stride values? Strides are basically the values indicating how much the spatial resolution of the feature map is reduced compared to the original image. And here I guess it's a little technical to go through the details, but keep in mind that the output here will be all the anchor coordinates together with the corresponding stride values. And now going back to this, assuming that now we have all the anchor coordinates and the corresponding stride values, what we do here is first we will concatenate prediction from all the 3 detection layers and try to reshape them so that they have the form batch size 4 times the. So this sum here is in fact the same as the number of coordinates plus the number of classes, or this is the number of outputs per anchor or anchor box, because we have 4 times number of bins plus the number of classes per anchor box, and this is simply the sums of all the height and width along all the detection heads, along the inputs of all the detection heads. Here we split out the prediction for the box and the classification score from X, and then we will process the box using the DFL in order to get the answers. So here what it basically does is it will process all the box coordinates using the DFL, and then it gives us the refined bounding box coordinates. So let's run this block and assume let's do a check here. We have version nano. Let's print out the number of parameters and print out the output shape. Note that in this case I feed in output 1, output 2, output 3 from above, which are output of the neck. So here we can see that the head has 0.89 million parameters, and the output of the head all have the same channel dimensions, which is this number 144 is equal to 4 times the bin size, that is 4 times 16 plus 80. That 80 is the number of classes. And finally, we are going to put everything together. At this point, building the model is quite simple. So we will initiate the attribute to be backbone, neck, and head. So for the forward pass, we feed the input through the backbone, feed it through the neck, and feed it through the head to get the output. So here I will initiate the model, the nano model, and print out the model together with the number of parameters. So the model here has 3.1572 million parameters, and if you go through the structure here, you will see that it is identical to the official model. So here maybe let's just remember this number 3.1572, and let's go back to the model that we load from the beginning. So Yolov8 official model here also have 3.1572 million parameters, and here is the model structures. If you compare them one by one, you will see that they match perfectly with each other. So at this point, we have recreated the Yolov8 nano model from the scratch. And for the next part, I'm going to overfit or train this model on one batch of data from Yolov 2017 dataset. Well, I don't have enough computation power, so I can only illustrate that the model works. So here for training of the model, the loss consists of three parts: the box loss, classification loss, and the so-called DFL loss. Well, box loss is the loss on bounding box coordinates. Classification loss means loss on the classification logics. And here the most confusing part is the DFL loss. At first, I was very confused between this DFL loss and the DFL in the detection head. In fact, they are different things. Even though they share the same name, but the DFL loss here doesn't come from the DFL in the detection head. Remember that the DFL in the detection head does not play a role in trainings. So this DFL loss, in fact, is integrated in the box loss. So how it works? Well, let's say for this loss, it is in fact a cross entropy loss functions. We need to have a target. We need to have a prediction. The target here is a distribution, which in fact is just a single value over 16 bins. Note that we have the range from 0 to 1, which are partitioned into 16 bins. So for example, if the target of the x coordinate is equal to 0.5, so this number will be smoothed between two bin centers. Right? So in this case, this number is in the middle of bin 1 and 2, so the target distribution will be half-half, and the rest are equal to 0. And now for the predicted distribution, it will be based on the output of bounding box coordinates. So these outputs together can be used to compute the probabilities for each bin. Let's say we have equal probabilities for all the bins. Now the DFL loss will be the cross entropy between these two. Well, so here I am going to in fact, I copy the computation of the loss from this GitHub repo, which is also the repo that I mainly based on the code in this video. So here you should go to this GitHub repo, and I copied the whole duty set from this repo. Here we will first, you will need to download the COCO dataset for this to work, for this to run, or later you can refer to my GitHub in order to see the details. So we will process the data, and we will take out one batch of the data. So here we have 18,049 batches. We will take out one batch among these 1,849 batches. So here I print out a few details like keys in a batch, which are classification, box, and index, batch shape, and so on. And here we are going to take out this single batch and try to overfit it. So we try to get the loss to 0. So here first we initiate the model. We set the loss function to be the function that is taken from the util that I take from the GitHub repo. Optimizer here is AMW, and I set learning rate to 0.5. And here is just the short chain routine in which we print out the loss for every epoch. So here our model has 3.16 million parameters. Because I am running on a CPU, it will take some time to run. I will be back after the training is finished. So we have finished the training after about 5 minutes, and we see that we start with a very big loss, that is about 15 million. However, the loss rapidly decrease, and after 4 epochs, the loss go down to 0. That is also the end of my video today. I hope you enjoyed. See you next time.